So we will continue on. We'll wrap up chapter 7 today, and we will talk about confidence intervals here. Okay. All right, so the idea behind confidence intervals is, okay, so let's just back up. And we start off with some kind of population, right? And of course we say, the population is too big for us to be observed directly, so what we do is we draw out a sample. Okay? So with a confidence interval, remember the population, the proportion that exists in the population is unknown, okay? So if we're talking about a categorical variable, the population has certain proportions in there. The proportions in the population are unknown. Okay? And but we get to observe a sample. We observe a sample, and we and the sample has a proportion p hat. Okay, so the p hat here just means sample proportion. So I know in our when we did linear regression, we said the hat over the y means it's our prediction for y. Here, the hat over the p means it's your sample proportion. It's the same hat, but they have different contexts here, okay? So here, p hat is our sample proportion. Okay? And the question is even though the population proportion is unknown, if we get to observe p hat, can we say something about the population proportion p? So p would be our population proportion. Okay, and so the basic premise is p is unknown. If we observe p hat, the sample proportion, can we say anything about p? And what do you guys think? Let me get this. 6, 7. Okay. So I mean, let me just make an example. Okay. So this time I've got a big tub of M&Ms. Okay. And this time I didn't count the proportion that exists in this big tub. Okay. But I take a scoop of M&Ms out. Okay. So I take a scoop out of the M&Ms. Okay. And then in my scoop, there are 200 pieces of candy, and we will say 36 are blue. So I think that makes it 18% blue. So p hat is equal to 36 over 200, 0.18 blue. Okay? All right, can I say anything about p, the proportion of blue candies that exist in the giant tub? this is the idea that we're getting at, okay? We only get to observe a sample. Even though we've only observed a sample, can we say something about the population, okay? And so this is kind of getting at the heart of statistics and statistical inference, in that we want to make conclusions based on limited data, okay? So what I hope is, and then in the rest of today's lecture, and I apologize, I forgot the clicker box today, so I can't ask you guys questions, but don't just leave though, all right? You'll make me sad. So what I hope is to show you kind of how all of this stuff that we've been learning so far, all of this theoretical stuff and all of that, how that comes together to kind of answer our question here, okay? All right, so to illustrate this, I'll make a little analogy, and so here, someone posts a photo, all right, and this is going to showcase my beautiful artwork here. This is, it's a dog, okay, and it's a dog on on a football field, okay, and he is standing at the 30-yard line, okay. So we'll say dog on the field, or dog at the 30. All right, but then, where is the owner is the question, all right? He is invisible. I don't know why I'm making these hashtags, but and has an invisible leash. Okay, so the dog's going on a walk. The owner is invisible, and there's an invisible leash, okay? And we want to know, where is the owner? Where is the owner, all right? So let me tell you that, a little bit about, we know something about the behavior of the dog, okay? This is a pretty good dog, all right? So we know the behavior of the dog. Okay? In that, the dog, well, he's on a leash, and it's an elastic leash, okay? Elastic leash, but most of the time, we'll say about 68% of the time, the dog remains within 1 yard of the owner. Okay? Sometimes the dog, finds something interesting to seek out. And so we'll say 95% of the time, the dog is within 2 yards of the owner. Okay? And then every now and then, we'll say 99.7% of the time, the dog will stray away, but 99% of the time, the dog remains within 3 yards of the owner, okay? And technically, because it's an elastic leash, the dog could end up really far away from the owner, but most of the time, that's not the case, okay? We know the behavior of the dog doesn't like to pull too hard against the leash, and so we know we have these kind of guidelines here. 68% of the time within 1 yard, 95% of the time within 2 yards, and 99.7% of the time, the dog remains within 3 yards of the owner, okay? So if we see the dog at the 30-yard line, can we say something about the location of the owner? Can we say for sure the owner is between 27 and 33? We cannot say for sure, okay, because it is possible that the dog is farther away than that, okay? But we can say something like this. We can say, so, you know, if we see the dog at the 30, okay, we can say, I am 95% confident that the owner is between 28 and 32. Does that statement seem reasonable? Okay. And so, does this guarantee that the owner is between 28 and 32? No, it does not guarantee that the owner is between 28 and 32. The dog could very well be at 33, could very well be at 33.5. I mean, and the owner could be at 33.5, or the owner could be at 26.5. The owner could be far away from the dog, but because we know the behavior of the dog, we can be fairly confident that the owner is within 2 yards of the dog, okay? So the owner could be far away from the dog. Okay. But if the owner is far away from the dog, then that means this picture was taken at one of those very rare occasions where the dog decided to stray far away from the owner, okay? Taken okay, and because we understand the behavior of the dog, we can be confident, we can say statements like, I am 95% confident that the owner is between 28 and 32. Okay? All right, so why did I bother telling you about this dog and his invisible owner and invisible leash? Well, what we can say is that the population, the location of the population parameter P is like the location of the owner, okay? So we can think of the owner as the population proportion P, okay? And this is unknown to us. Okay. However, the dog is our sample proportion P hat. Okay, and this is known to us. So we can see the location of the dog, even if, and the owner is unknown to us, okay? And what we learned earlier was in the central limit theorem, the central limit theorem says basically P hat follows the normal distribution. Okay, it follows the normal distribution, And what that tells us is that p hat most of the time is close to the population proportion p, okay? So p hat is usually very close to p. Or I'll just say close, not very close. We'll say p hat is usually close to p, okay? Sometimes you can get a p hat that is far away, but most of the time p hat is close to p. But most of the time, p hat, is within 2 standard deviations. Most of the time, we'll say about 95% of the time, is within 2 standard deviations of p. So we can say this, all right? So we know from the central limit theorem, all of this theoretic stuff, this basically tells us that the behavior of p hat follows a normal distribution, okay? And because we know p hat, the behavior of p hat follows the normal distribution, we can start making statements like, I am 95% confident that p is within 2 standard deviations of p hat, okay? So because we know this, we know about the behavior of p hat, we can say, I am, 95% confident that p is within, and it's technically not 2, it's 1.96, 1.96 standard deviations of p hat. Okay. All right. Does this make sense conceptually? Are we okay with how we arrived here? Okay. How big is a standard deviation when we're talking about the sampling distribution of p hat? We said the standard deviation is equal to the square root of p times 1 minus p over n, right? Okay. But there is a little bit of a problem here. And do you guys see the problem with this equation? Is that we don't know what p is, right? So p is unknown. P is unknown, so we're going to do our best guess, and we're going to plug in p hat. So we're going to just substitute p hat in for p, okay? And if you do all of the mathematical theory, this substitution is okay. It doesn't mess things up, okay? Like, I'm not going to try to prove that to you guys, but we're just going to say substituting in p hat for p, mathematically it works out okay in the long run, okay? And when we do numeric variables, we have to make adjustments when we do substitutions. But for now, it's okay. All right. And so the end result is something like this, okay? Okay. So, we observe a sample. Okay. With basically n observations. X quote-unquote successes, and proportion p hat. Okay? And so based on this, based on our sample, we can say I am 95% confident that the population proportion P is between, and on the low end, I'm going to start off at P hat and go down basically 2 standard deviations, 1.96 times P hat times 1 minus P hat over n, okay? And on the upper end, we would have P hat plus 1.96 times the square root of P hat times 1 minus P hat over n. And we end up with that. Okay. So basically, you know, on the, if you have a number line, whatever, you know, you observe P hat right here, and then you're going to go out basically 1.96 times your standard deviation, and then you'll do the same thing in the opposite direction. And we say, you know, now we can say we're 95% confident that P is between here and here. All right, yeah, basically our ends. Okay. All right. And I got, the way I got 1.96 was from our normal distribution, right? So this is for a 95% confidence interval. If I wanted to make, if I want to be more confident, let's say, if I want to be more confident that the value P is within my interval, should I make my interval wider or should I make my interval more narrow? I want to be confident that P is between the ends of my interval. Should I make it wider or narrower? Right, this would have been a clicker question, but it's, I don't have the box. What do you guys think? We would make it wider, right? Okay. So if we want to be more, confident that our interval managed to quote unquote capture the value of P, we would make the interval wider. Okay? It's basically just casting a wider net, right? You can be more confident about catching stuff if you cast a wider net. Okay? Okay, so you know, if I wanted to make a 99% confidence interval, okay? To to make a 99% confidence interval, basically, I'm going to, I've got p hat minus, and I'm going to just put in this value z, okay? Z star times p hat times 1 minus p hat over n for, and then basically I'm going to just combine the plus and the minus into one symbols here, okay? So instead of having to write from minus this to p hat plus this, I'm going to just combine the two into p hat plus or minus, okay? So, you know, combining both ends with the plus minus symbol. Okay? Basically, all I'm going to do is I'm going to adjust z star. Okay? We adjust z star so that in our in our normal distribution, when I shade everything in the middle, I have 99%, okay, which means the amount I have in the tail will be 0.005, and over here will be 0.005, okay? And if you look that up in your z table, you will get z is equal to negative 2.58, and z is positive 2.58. Okay? And so to make a 99% confidence interval, z star will be 2.58. Okay? And so you could look up basically any level confidence kind of using this same technique, right? And so again, you know, the way we ended up with 95% was that, you know, we want 95% in the middle, 0.95, which means we have 0.025 over here and 0.025 over here, and you get negative 1.96 and positive 1.96. Okay, and so I would say when you make confidence intervals, I don't know, because we have 5 fingers on our hand and we're base 10 decimal system, we probably use 90%, 95%, 99% most frequently, okay? And so really there's just like 3 numbers that you really need to know. Sometimes you can throw in an 80% interval. But I mean, if you want to make a 97% interval, you could. I would just say that's pretty uncommon, okay? 95% is probably the most common interval to make. So I'll say values of z star you should know. I would say for 99%, z is going to be 2.58. 95%, z is 1.96. 90%, if you look this up, you get 1.64, 1.65, so we just split the difference into 1.645. And then I guess 80% I'll throw in there also. Z is 1.28, okay? And again, you know, we would say we are blank % confident that P, the population proportion P, is between P hat minus, plus or minus, Z star times the square root of P hat 1 minus P hat over N, okay? So, you know, just write, for confidence intervals, use P hat in the standard deviation because P is unknown. right. Is that so far so good? All right, so let's go back to our M&M problem. And so we got our big tub of M&Ms. Okay, our sample is 200 pieces, 36 blue, so 0.18 is our p-hat. Okay, so I'll say make a 95% confidence interval for the proportion of blue M&Ms in the tub. Okay. So if I had a clicker question, I would make up some answer choices here, but I don't have the box. I apologize. I don't know. All right, so go ahead and figure this out. How many different colors of M&Ms are there? There's like blue and green. In the standard milk chocolate. 6? Blue, green, red, orange, yellow, brown? All right. I'm having too much fun coloring in. So apparently, like, have you guys heard of like grown-up coloring books? And they're like therapeutic and stuff. Apparently, there's like a huge, this increase in popularity for the grown-up coloring books is causing a shortage of colored pencils. So it's like colored pencil demand is an all-time high. Okay. All right. What did we get for our answer here? D? Is that what we got? Okay, that's what I got. All right, so again, our intervals, we put our best guess for the value of p makes sense to be p hat. And then we're going to have basically p hat minus z star times the square root of p hat times 1 minus p hat over n. So, you know, when I plug in these values, I get 0.18 minus 1.96 times 0.18 times 1 minus 0.18 over 200. And then I got 0.18 minus 0.053 to basically 0.18 plus 0.053. So I get 0.127 to 0.233. Okay? So this is our 95% confidence interval. And I would say I am 95% confident that the proportion of blue M&Ms in the tub is between basically 12.7% to 23.3% blue M&Ms. Okay. So I'll let you guys finish writing this, and then I'm going to flip over to the next slide. Is this all right? Okay. So we'd say, you know, I am 95% confident that the proportion of blue M&Ms in the tub is between 0.123. Wait, what did I have? 0.127? Yeah. Okay. And 0.233 and 0.233. Okay. All right. Let me write a few things that we. So I was going to make true/false questions. Here, I'll just go ahead and make these, and there's just no buttons to push. Okay. All right. So true or false? So if we had a clicker, falsa. We would do this, okay? It would be there is a 95% probability that the proportion of blue M&Ms in the tub is between 0.127 and 0.233. Okay? So there's a 95% probability that the proportion of blue M&Ms in the tub is between 0.127 and 0.233. What do you guys think? True or false? So think about this. I'm going to pretend like the timer is going on here. You guys are clicking away. What do you guys think? What do you guys think? You can talk about this with your neighbor. Okay, I'm going to give you the answer now. All right, so what do you guys think? Those who raise your hand, true. Some? And false? Okay, all right. And the answer is false. Okay, why is it false? What? All All right, so this is a bit of a trick. It talks about probability here, okay? And at least for frequentist, our frequentist view of probability, the proportion of blue M&Ms in the tub is a fixed thing, okay? It's a known quantity, P, okay? There's no uncertainty about P, okay? So here, let me illustrate what I'm talking about here. Oh, I lost my quarter. Okay, all right. So I've got an invisible quarter here. Oh, okay. Well, all right. So, you know, if before I flip a coin, I can say, what's the probability that this coin will land heads? And you would say 0.5, right? Okay, so I flip it. Okay, it's landed. And then I ask, what's the probability that the coin landed heads? And you would say, and you guys still say 0.5, okay. All right, so pretend the coin has landed. I'm looking at the coin. I now see how the coin has landed. You guys haven't seen it, and I ask you again, what is the probability that the coin has landed heads? And then now you guys are like weirded out. The truth is the last two questions, before I flipped the coin, it was a valid question. What's the probability that the coin will land heads? That's a valid question because the coin has not been flipped. There's uncertainty in this thing. Once the coin has landed, the question of probability no longer makes sense. The coin has landed. It has either landed heads or it has landed tails. There's no uncertainty associated with the coin flip or the outcome. And so it doesn't make sense to ask you about the probability that it landed heads. You don't know whether the coin has landed heads or not. So all you can say is, I am 50% confident that the coin landed heads, or I'm 50% confident that the coin landed tails, but the question of probability no longer makes sense, okay? And so when we're talking about the tub of M&Ms, P is a fixed value, okay? P is some value that is unknown to us, but it's a fixed value and there's no uncertainty about it, okay? The amount of M&Ms in the tub is not uncertain. It's some number. The number of blue M&Ms in the tub is also another number. So we could get the actual value of P, and there's no uncertainty about it, okay? It's fixed. There's no uncertainty. Okay, so it does not make sense to talk about the probability of P, okay? Probability of P, whatever, okay? So either P is in the interval or it's not. We can be 95% confident that P is in the interval based on what we understand about P hat and all of its central limit theorem and all of that. But to talk about the probability of P, that does not make any sense there, okay? All right, we'll end here today. We'll continue on Wednesday. And you guys have an exam on Friday. So this stuff is not on the exam, okay? It's just through the stuff I covered last week.